invite Dr. Rakiyappan from the Bharadiyar University to chair this session.
So we have an invited third invited of a second day of the symposium, Professor Dr. M. Guru Prem Prasad, IIT Guwahati. Professor M. Guru Prem Prasad works in the area of complex dynamics and fractals. So he received his doctoral degree from IIT Kanpur in 1998, and he has been working as a faculty member in the Department of Mathematics, IIT Guwahati, since from 1999. He has guided several master theses and doctoral theses at IIT Guwahati. His research work is mainly towards the study of dynamics of holomorphic functions. He has carried out research in the area of fractal interpolation functions. So I welcome you, sir.
I just want to present about the dynamics, complex dynamics of holomorphic functions. Especially I would like to talk about the transcendental functions. Okay. So thanks to the organizer for inviting this symposium and especially giving talk on this complex dynamics. Okay. So just a little bit I tell about what is about complex dynamics, then I will go to the work, what we do. Okay. So if you want to state it is a very simple language. Here the notation is C hat, which is basically we denote as complex plane plus point at infinity together. It's called extended complex plane. So we deal with the analytic functions, okay, and then this Fn is basically denotes the n times composition of the function f. Okay. So in complex dynamics or iteration theory, the goal is to understand what happens to this sequence of iterates. Okay, especially as n tending to infinity for each point. That is the simple language if you want to state the problem. Okay. So start with the initial point z0, that is then you compute the f of z0, f of z0 and so on. So this sequence is called sequence of iterates, or we call it as orbit or forward orbit of the point z0. So basically we want to study the behavior of the forward orbit of each point in the complex plane. So the actual things started with basically the dynamical, this is basically discrete dynamical system. Okay. So it started with Stardust work, and then especially it took a momentum when the two French mathematicians, Julia and Fatou, they started more on studying about the rational functions and transcendental functions. Okay. Then later on in 1955, Ian Baker, he has developed the theory of the entire functions, especially entire transcendental functions. Okay. So in between the discovery of Mandelbrot set, so that made it more beautiful graphics related to the this dynamical system especially. So that makes a more kindle the interest again. Okay, that is the one. So if you want to see the history, you can see these are the two articles. You can find out the history of this complex dynamics. Okay. So as a starting to think, even Cayley in 1879, he was studying about the this Newton's Fourier method, what he calls. So what he told that you start with the initial points, okay, so where it is to be taken, so anywhere in the region, so that we arrive this ultimately lead to the root of a polynomial. So where you start the initial point and do the equation, whether it is approaching to the root of the polynomial or not. Okay, so that is the question he want to look at as a globally in the sense of iteration. Okay, so that one, if we see Newton's method, okay, you start with the initial point, and this map we call it as Newton map, and we are going to study about the iteration of this map or dynamics of this system. Okay, so as if we want to say simple results related to Newton maps, and if you say if the alpha is a simple root, then this iterative scheme, this iteration converges quadratically, and if it is a multiple root, it converges linearly. So these are the results we know from our numerical analysis things. So what we are looking at, alpha is the root of the polynomial, then we are looking out, we want to find out set of all points in the complex plane or extended complex plane for which this Newton iterates converges to alpha. Okay. So this is name is called, this set name is called basin of attraction. Okay. So now If it is a polynomial of degree n, then there will be n roots will be there corresponding to the n roots, there will be a basin of attractions. Then take their unions, and then in what we can say about its complement. Okay. So this complement set is basically going to be the chaotic region or chaotic set. Okay. Whereas this one is a stable sets kind of thing. Okay. So in that Cayley proposed this one, especially the quadratic polynomial, it was done thing. For example, z square minus 1 is the polynomial you take, you do the Newton's method. Then the result is that if you start your initial point in the right half plane, real part of z greater than 0, right half plane, then it will converges to the positive root. If you take your initial point in the left half plane, real part of z less than 0, then that Newton iterates will converges to the minus 1, okay, negative root. If you take your initial point on the imaginary axis, it will be chaotic, it won't converge at all. Okay. So that is the one about the very simple one, z square minus 1. So with the help of this function, by doing the conjugations, one can make a result for the any quadratic polynomial, what is the basin of attraction. Okay. So this is some pictures you can see in net also. This is some cubic polynomial, what are the basin of attractions. So cubic polynomial which having 3 distinct roots. So where if you take the initial point in this blue region, it will convert to one of the root, green region it will convert to another root, and similarly the red region. Okay. So this is the basin of attraction for 3 distinct roots of the cubic polynomial. Okay. So these some more pictures are there. So this is all about the story, how it started or how the Cayley work was started beginning at the thing. And when these 2 French mathematicians, Julia and Fatou, so they started studying as a complex function, look it as a rational function or a transitional function, how this iteration goes. Okay. So here, while studying the dynamics of analytic function, the approach of study is totally different than your nonlinear dynamics. Okay. So nonlinear dynamics function as a function of Rn to Rm, if you study how the dynamical is totally different techniques. But if you have function, analytic function, the iteration theory or dynamical system study is totally different approach we have. Okay. So this approach is mainly based on the concept of what we call it as a equicontinuous or normality. Okay. So basically it's something, if a given sequence of function, when it will have a convergence subsequence, especially uniformly convergent subsequence. Okay. So that concept is used here as a basic theory. Okay. So that one is called, especially given by Montel, this concept is called normal family. Okay. So how this normal family is defined is, you take a family of analytic functions on a domain D, and this family is said to be normal if for each sequence of functions in this family contains either subsequence which converges uniformly to a limit function on every compact subset of T omega, or it has a subsequence which converges to infinity on every compact subset of omega. So any one of the things will happen. Okay. So that will every such sequence you take it from that family, then we call it as the family is normal family. So this is the basic definitions, the normality. So this is the one is used as a basic object or basic concept in the dynamical system of complex functions. Okay. So to explain this definition, you can see this example. I am taking the family. This is family itself is a countable family, countable collection. Fn of z equal to z power n. I am taking the domain as a open unit disk mod z less than 1. So then you take any sequence from this family. Okay. So that will converges to 0. Of course, that you can show that that convergence also uniform on a very compact subset of open unit disk. Okay. So for this function, the open unit disk in which this family is normal. Similarly, the same function family I am taking. So that family is also normal in mod z greater than 1 because it tends to infinity uniformly on every compact subset of mod z greater than 1. Okay. So this family is normal in mod z less than 1 as well as mod z greater than 1 also it is normal. Okay. And of course it is going to be not normal on mod z equal to 1. It won't happen. Okay. Similar another example, if you want to understand this thing, this is a family c times e power z, where little c is varying over real number you can take, or you can take even complex numbers also. So this family is the uncountable family, okay, uncountable family of function. So to check whether this family is normal or not, what you have to take, you have to pick a sequence of functions, okay. Suppose I picked a sequence of function cn times e power z, okay. So then depending on cn, the result will be there. Suppose this cn is a bounded sequence, okay. The cn is a bounded sequence, then it will have convergence subsequence by real number thing, Boltzmann-Weierstrass theorem. So that c1, there is a convergence subsequence, you will get it. Suppose that cn is not bounded, it's unbounded sequence, then obviously it will tend to infinity. So that time the that sequence of function will converge to infinity. So this family is normal at all points of C. So this is all about the normality definition, how these examples thing. So for example, this family, if we take it n times z, which is a countable family. So this family in the open unit disk, it is not normal. Okay, why it is not normal? Because at non-zero points it tends to infinity, at 0 it tends to 0. So if you take any compact set containing 0, that convergence cannot be uniform. Okay, so this family is not a normal family. Okay, so this is these are the examples telling about the normal families and non-normal families. Okay. So now the basic objects are studied in the complex dynamics is the Fortu set and Julia set. So how it is defined? The Fortu set of a function f is defined as the sequence of iterates is normal in some neighborhood of z. Okay. So normally we take the entire function, so this sequence of iterates is well defined. If we take a meromorphic function, then we will add an extra condition that the sequence of iterates fn is defined and normal in some neighborhood. We will add that condition. Okay. And its complement of the Fortu set is called Julia set. Okay. So in nonlinear terminology, this Fortu set is going to be a stable set, and the Julia set is going to be a unstable set or chaotic set. Okay. So this is the basic definition in complex dynamics, which is defined in terms of normality. Okay. So to understand these definitions, I take this function f of z equal to z square. Okay. So for this function, I want to determine what is Fortu set and Julia set. So Fortu set means the set of all points at which this family of sequence of iterates form a normal family. Okay. So already you can see that mod z less than 1, this sequence of iterates converges to 0. Mod z greater than 1, the sequence of iterates converges to infinity. And mod z equal to 1, the sequence of iterates just goes on mod z equal to 1. It doesn't converge anywhere. Okay. So for this function, the Fortu set is basically mod z less than 1 union mod z greater than 1. Okay. So then its complement is basically mod z equal to 1 is a chaotic set or Julia set. Okay. So this is a very simple one, z square. The Fortu set is which is the union of two domains, mod z less than 1 and mod z greater than 1, and the Julia set is basically mod z equal to 1. But even if you simply small perturbation about thing, if you take z square plus c, then the Fortu set and Julia set become become much more important. Okay. So in this case, very simple, you can easily find out this is the Fortu set and Julia set. But if you take a some function like z square plus some constant, so then the determining Fortu set and Julia set become highly complicated. Okay. So these are the basic properties of these sets. Okay. Fortu set is the open set, Julia set is the closed set, of course, and it is a non-empty set, it is a perfect set, it has an empty interior unless it is equal to C hat. Okay. So and further, these two sets, Fortu sets and Julia sets, are completely invariant. Okay. These are invariant subsets. That is both sides, f of u is contained in u and f inverse of u is contained in u. That is forward invariant as well as backward invariant. So these two sets. Okay. And so then this terminology we will use it. Suppose some point is not an exceptional point, means basically the backward orbit of z0 is finite, then it is called an exceptional point. So the first characterization about this thing Julia set is the backward orbit of a point in the Julia set is a dense in Julia set. Okay, so that's why you can get the thing. In case of transcendental entire function or transcendental meromorphic function, the point at infinity belongs to Julia set, whereas in case of polynomial, this infinity belongs to Fortu set. So that makes more complicated in case of transcendental functions. Okay. So another things which plays important role in the system of complex dynamics, the periodic points. Point is said to be periodic of with period p, f p of z naught equal to z naught. Of course, we take the smallest positive integer p such that f p of z, so that is called prime period or thing. And for this periodic point of period p, you define this number lambda, which is f p prime z naught, which is called multiplier or eigenvalue. So depending on this multiplier, these periodic points are classified. If mod lambda is less than 1, it is called attracting. Mod lambda equal to 1, it is called neutral or indifferent. Mod lambda greater than 1, it is called repelling. Okay. Further, we classify this neutral as when lambda equal to e power 2 pi I alpha. Alpha is rational, it is called rationally neutral. When alpha is irrational, it is called irrationally neutral. Okay. So these classifications will help us to what role it is playing there. Okay. So for a periodic point, the forward orbit becomes finite. After p plus 1, it will start repeating. Okay. The periodic points, the forward orbit is basically finite set thing. So if a point is attracting, then we call it this is attracting cycle. If it is a repelling periodic point, then we call it as repelling period cycle, etc. Okay. Sometime it may happen that certain points are not initially periodic, but it will later on it become periodic. Okay. So that also there, such point we call it strictly pre-periodic. Otherwise, the general definition of pre-periodic is for some positive integer, it become f1 of z naught become periodic. Okay. For example, this function z square minus 1, minus 1 is periodic, whereas z equal to 1, which is strictly pre-periodic. Okay. So it's a 1 become mapped to 0, 0 mapped to minus 1, then minus 1 become periodic. Okay. So the attracting periodic points always lies in the Fortu set, repelling periodic point lies always in the Julia set, rationally neutral periodic point lies in the Julia set, but irrationally neutral periodic point can happen anything depending on the function. Okay. So the first characterization about the Julia set is the Julia set of a function is the closure of repelling periodic points of f. Okay. So this is the main characterization about the Julia set. And then this is about the story about the Julia set. This is one characterization. There is another characterization backward. You take any point in the Julia set and trace its backward orbit, that will be dense in the Julia set. That is the second characterization. So now come to the Fortu set, which is a set of a non-monality or set of stable sets. So these are a open set. So it's take the maximal open connected subset of this one is called component or Fortu component. So this Fortu component is periodic if there is a p such that fp of u is contained in u. Okay. Similarly, pre-periodic we do it, and sometime it may happen that it is never become periodic. Okay. So that is that such component we call it as wandering if it is not pre-periodic. That is fm of w intersection fn of w is equal to mt for any m1 n in natural number m not equal to n. Okay. So now Fortu set, these are the situation. Either it is the components become periodic, or it become eventually periodic, or it is never become periodic. These are the three possibilities. Okay. So either periodic, or it is become eventually periodic, or it's never periodic. So the never periodic is basically wandering. This is a much more complicated case. Okay. And 1982, Dennis Sullivan proved that for a rational function, this wandering domains does not exist. So this is a very breakthrough result in case of dynamical system of rational functions. So he proved using the techniques of quasi-conformal mapping. Okay. So the rational function cannot have wandering domains, and hence of course the rational function includes polynomials also. Okay. But it was Hermann in 1985 produced that transcendental entire function for which there is a wandering domain. Okay. So, for transcendental entire function there is a possibility of wandering domain, but in case of entire function, if you say polynomials, polynomials will not have a wandering domain. So, there is a major distinction between polynomials and transcendental entire. Okay. Polynomials function will not have a wandering domain, but transcendental entire function may have wandering domain. So, similarly, comparing with a meromorphic function, the rational function does not have a wandering domain, but transcendental meromorphic may have wandering domain. Okay. So, now this periodic point for two components, it is classified that they will have they will take any one of these forms only. Okay. So, these are the following 5 possible forms. One is called attracting domain, another one is parabolic domain, another one is Siegel-Dix, Hermann-Ring, Baker domain. Okay. So, these are the 5 possibilities for the for two components. Okay. So, there also it is proved that for polynomials, the last Baker domain and Hermann-Rings does not exist. For rational function, Baker domain does not exist, Hermann-Ring exists not for the entire functions, etc. Okay. These are the results about the part two components for polynomials and rational functions, etc. So, then what is attracting domain or attracting basin? It contains the attracting periodic point. Okay. So, it contains attracting periodic point and the nearby points whose orbit will be attracted to that. Okay. That is why it is called attracting domain. And if its derivative is at that attracting point is 0, it is called super attracting domain or Botcher domain it is called. Okay. For example, Z square, Z equal to 0 is a attracting fixed point, not only attracting, it becomes super attracting because the derivative also 0. Okay. So, then mod Z less than 1, it is a for two component, this for two component containing this attracting fixed point. So, it is attracting domain for the for two set of this function. Similarly, parabolic domain, in this case there is a periodic point which is neutral periodic point which lies on the boundary, not in the interior, it lies on the boundary. So, such thing is called parabolic domain. For example, this function, the 0 is a rationally neutral function point. So, that lies on the boundary of the for two component. Okay. So, it is called parabolic domain or Liu domain. And then Siegel-Dix and Hermann-Rings are basically that for two component you can have an analytic homeomorphism between unit disk and that component, then it is called Siegel-Dix. If you have analytic homeomorphism between that component and annular domain, then it is called Hermann-Ring. Okay. So, these are sometimes called as a rotational domains, and here the limit function of sequence of iterations is a non-constant. Whereas this earlier case, all the points will converges to the forward orbit of all points converges to this neutral periodic point. Similarly, here the forward orbit of all the points converges to the attracting point. So, the limit function is constant in this case and in this case. But whereas in this Siegel-Dix and Hermann-Ring, the convergence subsequence which has a non-constant limit functions. Okay. So, the last one, there is a possibility of a for two component for which there is a point Z star on the boundary such that the sequence of iterates converges to Z star, but S of Z star is not defined. So, that is called Baker domain or sometimes called domain at infinity. So, if you take the obviously you are looking at a point Z star for which the function is not defined. Okay. So, polynomial it is everywhere it is defined, even at infinity also we take P of infinity is equal to infinity. Okay. So, for polynomial there do not have a Baker domain. Okay. But in case of transcendental entire function, there is a possibility that infinity become essential singularity, so that function is not defined. Okay. So, the Baker domain is possible for transcendental function, but it is not possible for the polynomials. So, this is the one first example Z plus 1 e power minus Z which has a for two Baker domain was domain at infinity is given by Baker. So, later on in honor of him we are calling as Baker domain. Okay. So, and then another thing is about the Julia set. It may happen that for polynomial FOR2 set is non-empty. So Julia set is non-empty, both are non-empty. Okay, so that Julia set becomes proper subset of C. Okay, it cannot be equal. Okay, but in case of rational function, there is a function produced and for which the Julia set become entire complex plane. Okay, so the chaotic set become whole of complex plane. That happens for rational functions. Sometimes it happens for transitional function, but it never happens for polynomials. Okay, so and Divani produced this function lambda times e power z, for which he showed that lambda greater than 1 by e, the Julia set become entire complex, extended complex plane. So it's called actually lambda less than 1 by e, it is a nowhere dense subset. When it is lambda crosses this parameter, it becomes entirely equal to extended complex plane. So that phenomena we call it as chaotic burst. Initially it is nowhere dense subset. When it crosses this critical parameter 1 by e, it becomes exploding and equal to C hat, and hence it is called chaotic burst. Okay. So another two things are which are influencing this dynamical thing, iteration theory. One is critical value, another one is asymptotic value. Okay. The critical value is defined like this. First of all, the derivative is equal to 0 at some point z naught, and the function value at z naught is called critical value. And asymptotic value, especially we are looking for finite asymptotic value. There is a continuous curve gamma t along which gamma t tends to infinity, the function value tends to a finite complex number. Then it is called asymptotic value. For example, e power z, you take the negative real axis, you take it. Along negative real axis, e power z approaches 0. So 0 is the asymptotic value for exponential function. Okay. Whereas sin z has no asymptotic value, only it has critical values. So this critical values and asymptotic values plays important role. The reason is at the critical value, the function fails to be 1, 1. Okay. So the inverse function has a singularity. So you have many branches you will get. So that's why it's called, under the name we gave it as a singularities of F inverse, these critical values and asymptotic values. So how they play important role in the dynamics is, these are the results telling about that thing. If Z naught is an attracting periodic point of F, then the basin of attraction contains at least one singular value. Okay. Similarly, parabolic domain contains at least one singular value, and Siegel-Dex and Hermann ring, the boundary of this U is contained in the closure of the forward orbit of singular value of F inverse. So basically what we do look at to study the dynamics is, first of all try to locate where the periodic points and try to locate the singular values, and then you decide what is happening to the forward orbits of singular values. Okay. So with this information you can able to infer that FOR2 set will be contains only this component or this kind of components, or this kind of components is not possible. We can arrive at such conclusion. Okay. So that is the way these results are very much useful to determining the nature of the FOR2 components, or how many FOR2 components are there. Okay. So coming to the transitional entire functions, now the present work is basically it's become more advanced. So we, depending on the singularity F inverse, that is asymptotic values and the critical values, as in this closure, we take it as SF. Okay. So if this SF is bound finite set, then we call it as class S. This SF is a bounded set, then we call it as class B, Ehrman-Lubitsch class. And then if every element of SF belongs to some basin of attraction, then we call it as class H, which is hyperbolic class. Okay. So now because the number of singular values are finite, then tracing the forward orbit of these finite number of singular values somewhat easier. Okay. It is not always true, but somewhat you can be able to track it. If it is bounded, then again depending on the mapping property of F, where this bounded set get mapped, etc., we can do it. But when these sets are unbounded, then definitely the dynamical study become highly complicated. We may not able to determine the dynamics. Okay. So the forward orbit of singular values is basically tending to infinity, then the Fatu set become empty set. That is, Julia set become entire complex plane. So that is the result is used by Divani, and then he proved that if lambda greater than 1 by E, this lambda times e power z, the Fatu set is empty, Julia set is equal to entire complex plane. The proof for this thing, I already told e power z has only one asymptotic value. 0 is the only asymptotic value. So then tracing the forward orbit of 0 is the only requirement. So the 0 forward orbit of 0 tends to infinity if lambda greater than 1 by E. Okay. If lambda less than 1 by E and the forward orbit of 0 goes to some basin of attraction, so that is the one there. So tracing the forward orbit that way, it is easier to determine the dynamics. Similarly, class B, class S has certain components are not there. For class S, there is no wandering domain. So the major headache is gone. Determining wandering domain is a very difficult task. So that is gone for the class S. Class B, no Baker domain is there, but there is a possibility of wandering domains also there. But certain conditions, you can exclude the wandering domains. Okay. So similarly, the class B also some more results are there, and depending on the hyperbolic things, what happens, okay, especially what kind of Fatu components are there. Okay. To simply explain, I already told this is like exponential function, lambda times e power z. It has only one asymptotic value 0. So that 0 forward orbit of 0 goes to a basin of attraction, and hence for 0 less than lambda less than 1 by E, the Julia set become nowhere dense subset. Lambda greater than 1 by E, the Julia set become extended complex plane. This phenomena we call it as a chaotic burst. Okay. So when lambda less than 1 by E, the Julia set looks like this. When of course color pictures are given, and then when lambda greater than 1 by E, it becomes chaotic burst. It is equal to the entire complex plane. Okay. So these are the functions we have studied, and some functions are not in class S also, some functions are in class B also, but still we are able to trace that, and we are able to show that it has a bifurcation, it has a chaotic burst, etc. So these are the things we have studied. Of course, some more functions also we have done, and this is one function recently one of my students is working. This is the entire functions. This is not in any of the class. The set of all singular waves become unbounded. So tracing forward orbit becomes difficult, but fortunately we can able to track it because all of them are lies on some set straight lines. So we can able to track it. Okay. So it has a certain parameters. It has a fixed point. Certain parameters it has a does not have attracting fixed point become repelling and etc. So that basically gives the period doubling bifurcation what we say. Okay. So a periodic point initially it was attracting, then it become repelling. So at that time repelling, it become repelling. There is another two periodic point of period 2 is coming as attracting. Okay. So that is called period doubling bifurcation occurs in this function, especially these parameters -1 and -√5 where the change in the nature of the dynamics are occurring. Okay. So that is at lambda equal to -√5, it become period doubling bifurcation. So these are the things. Of course, you can now the latest work is mainly by these mathematicians, especially Walter Bergweiler, Lesser Rempe, and Divani. So mainly they are now working on about the wandering domains and Baker domains. Okay. So then the further wandering domains they classified with so many depending on the singularity nature. So the work on wandering domains for a translator functions or translator meromorphic functions are mainly carried out by these things. Okay. So that's all something. Of course, these are the pictures you can see. This chaotic set become fractals. This is a Mandelbrot set. So Mandelbrot set is a set for which it is taken for z square plus c, that quadratic polynomial, for which the Julia set is connected. Okay. The set of all parameters c for which the Julia set of z square plus c is connected is basically in Mandelbrot set. The Julia set for which it is not connected that will be outside. Okay. So this is a self-similarity structure is there for this Mandelbrot set. Okay. So these are some of the Julias. and this is a Julia set of this polynomial z square minus 0.75. That is boundary is the Julia set. The white color is the one of the basin, blue color is another basin. So the boundary become the Julia set. So that also looks like a self-similar structure is there. So that's why we call it as fractals thing. So fractals arising from dynamical systems, these are the things. Yeah. Any questions you can ask.
So thank you, sir. Thanks for your nice talks. Any questions?
Yeah, closure. Forward, that is critical values, asymptotic values plus its closure.
So why you want to take a closure, sir?
Suppose some function has infinitely many singular values or infinitely many critical values. So then
Those means you are saying that singularity of f is need not be always closed.
yeah.
That's one thing. So that you mentioned that S of f equals singularity of fness of closure.
Yes.
So do you have any idea about that? How to find the S of f2?
S of f2.
Is there any relation between S of f and S of f2?
Because see, basically we don't try to look at things because the Julia set of f1 equal to Julia set of f. Similarly, for2 set of f1 equal to for2 set of f. So either you study f or f2, it's same. So you don't need to look at the.
No, I want to view in the set theory point of view.
Okay. So f2 will be 2 times composition there inverse you are asking.
So is there any relation between S of f and S of f2?
S of n. There is, I don't know, no idea. Because it's depending on the function, we cannot say where it get mapped.
Okay, sir. Thank you.
Any other questions?
Sir, in case of basin of attraction, actually what we are getting, sir? Just I would like
So
to know.
basically, if you take any, your initial point lies in that basin of attraction, okay, then the iteration converges to that point. Forward orbits converges to that point.
Okay, and means what that picture shows us?
See, basically, okay, this picture is basically an international thing.
No, I'm not saying this picture.
Okay,
sir.
okay, anything. So, for example, I told the z square function, f of z equals z square, 0 is the attracting fixed point.
Right. Sir.
Okay. So, the nearby points of that attracting fixed point, okay, their forward orbit will converge to that point. So, that what is the possible domain, set of all points for which the subsequence has this limit. Okay. Or you can say that the normality where around that point. Okay. So, the neighborhood, the attracting fixed point you have taken. So, the forward where that sequence of iterants become normal at that point. Okay. So, the largest possible domain about the Z0 is the basin of attraction.
Thank you, sir.
I'm Guru Prem Prasad from Indian Institute of Technology, Guwahati, to accept our invitation and deliver the invited talk in our symposium. Thank you, sir. And also I thank Dr. Rakiepan for chairing this session. Now I request Dr. Rakiepan, sir, to hand over the memento to our invited speaker. Now I request Dr. Tanmay Shom kindly give the. No, sir, please. You can. Thank you, sir. So, very good afternoon, everyone. So, I request Dr. Ashish Saha from Sikkim Manipal University to chair this session. I handed over this session to the Dr. Ashish Saha from Sikkim Manipal University. Thank you, sir.
I welcome all the participants in this session. Our speaker, Dr. Rakiepan from Bharatiya University, India. Dr. Rakiepan completed his BSc in the field of mathematics during 1999 to 2002 from Sri Ramakrishna Mission Vidyalaya College of Arts and Science. He has completed master degree in mathematics from PSG College, Coimbatore. He was awarded Doctor of Philosophy in 2011 from Department of Mathematics, Gandhigram Rural University, Gandhigram, Tamil Nadu. His research interests are in the field of qualitative theory, cryptography, neural networks, complex systems, fractional order systems. He has published more than 200 research papers in reputed international journals. He was the recipient of highly cited researchers 2019, 2020, 2000 and 2021 by Clarivate Analytics Web of Science. Now he is working as an assistant professor in the Department of Mathematics, Bharatiya University, Coimbatore. So I like to request you, sir, you please start your presentation.
Okay, thank you, sir. Thanks. The title of my talk is Stability Analysis of Time Varying Time Delay Systems. So for the past 18 years, so I am concentrating this area, and we have done several interesting works. And we published in reputed international journals. So like IEEE transactions on neural network learning systems, IEEE transactions on cybernetics, IEEE transactions on system and cybernetics with systems, and IEEE transactions on fuzzy systems. So the stability theory has so much applications. So now I start with the definition. The stability generally refers to the behavior of a mathematical object, systems or solutions over time and are under perturbations. So the concept of stability is used to describe how changes in the input or the initial condition after the behavior of all mathematical entity and whether it remains bounded or approaches a certain equilibrium state. So when dealing with the differential equations, either ordinary differential equations or partial differential equations, the stability issues depends only on the initial conditions. So if for any initial condition the solution of the equation are bounded, then it is said to be stability of a differential equation. So it is used to describe buildings or structures that won't collapse or fall down. So the stability has such application starting with this one. So moreover, a cyclic pattern of a earth rotating systems. It is also an interesting example. So here you can see the stability analysis in the cyclic pattern for earth rotation. So here, so this is the direction of the earth rotation. So this motion is a periodic motion, and also it is also a stable motion. So this is a simple example for the stability analysis in a cyclic pattern. So here we can see the physical interpretation of a stability issue. So in the today's world, there are many ways to study how the things stay stable in mathematical equations. So we have methods like Lyapunov stability, asymptotic stability, exponential stability. So naturally these are the interesting factors which are using in the recent times, the finite time stability, fixed time stability, prescribed time stability, and also the predefined. And there are so many other stabilities also. Stability definitions are also available in the literature. So the basic thing is the Lyapunov stability. So the Russian mathematician A.M. Lyapunov in 1892 he introduced the Lyapunov stability in the Chinese version, and afterwards it was extended in the English version. So we are using that English version as the basic concept of the basic theory of the Lyapunov stability. And there are remaining stabilities like asymptotic, exponential stability belonging to infinite time stability, which means the stability can reach when the time tending to infinity. For example, So this is the it falls, this diagram shows it falls under the definition of a Lyapunov, the stable in the sense of Lyapunov. So you start any initial condition in this neighborhood, the trajectory of your system remains belonging to this neighborhood, the outer neighborhood. So you pick an initial condition from this inner neighborhood, and then as time goes on, your trajectory lie within this outer neighborhood. Then we can say that the system is stable in the sense of Lyapunov. So in this case, you can see that. So you have an initial condition from the inner neighborhood, and it starts from this one, this initial condition, and then again it moves close to the equilibrium point x naught. So it converging, so it means that it converging to the equilibrium point x naught. So therefore this is a concept of asymptotic stability. And then the third one is if you start an initial condition from your inner neighborhood, it moves far the trajectory of the system far from your equilibrium point. Then we can have this is a motion of an unstable condition. Okay. So compared with the asymptotic stability and exponential stability means that it converging over time tending to infinity, it converging very fast in an exponential manner. So therefore we can call this as an exponential stable. So the asymptotic stability and exponential stability, the stability analysis in finite time has an obvious advantage in practical applications. So we do not want to wait so much time when time tending to infinity. At the time of infinity, what will happen? So we do not want to wait those times. So we have to fix a time, a finite time. So in that case, so the finite time stability is very, very important for the study of physical systems. So there are two categories of concepts: stability over finite time interval. So one is the fixed finite time stability, and the another one is the fixed time stability. The finite time stability is that means that the system converges within a finite time interval for any initial value. So if you give any initial value, so your system remains stable when you fix a finite time. Within a finite time, the trajectory of your system moves towards the outer neighborhood. So it maintains the stability. So therefore this stability is called the finite time stability. So and the other one is the fixed time stability. So in this case, so the same finite time, the fixed time stability is itself a finite time stability, and also we want to estimate the settling time for all initial conditions. If you want to give any initial condition, the system will be finite time stable, and also you have to calculate the settling time. So this is the difference from difference from the finite time stability. So additional one more thing is that we want to calculate the settling time for fixed time stability. Although the finite time stability concepts represents a significant advantage over finite time stability, it is often fixed time stability concepts represent a significant advantage over finite time stability. The reason is we want to estimate the settling time. So it is often complicated to find a direct relationship between the tuning gains and the fixed time stabilization time. So to overcome the above, it is necessary to consider another class of dynamical systems that exhibit the property of predefined time stability. This is the third one. So in the finite time stability concept, we have the third definition. The third definition is called the predefined time stability. Furthermore, it is in the subsequent manner, the prescribed time stability undergoes the achievement of a specific level of stability with the designated time frame. So in this talk, so I am concentrating the finite time stability as well as the finite time contraction stability based on the definition of Francesco Amato. So he was a French mathematician. He was done enormous work, and he has published so many works in IEEE transactions on automatic control as well as Automatica. So I am concentrating his only. So there are two types of definition for finite time stability. So I am particularly concentrating the definition which is related to or which is due to Francesco Amato. So consider a non-linear initial value problem. Consider a initial value problem. So this is a non-linear differential equation, system of non-linear differential equations. So here you can consider the system with the initial condition x of t naught equal to x naught, and your state will be belongs to Rn. So we can give the following formal definition which restates the original definition. So this is the definition of stability in the sense of Lyapunov. The system 1 is said to be stable in the sense of Lyapunov if for all epsilon positive there exists a delta positive such that norm x naught is less than delta. Norm x naught is less than delta. This delta depends on epsilon and t naught. Then implies that x of t, norm x of t is less than epsilon. So for all t greater than or equal to t naught. So in this case you can see. So this is the delta neighborhood. The inner neighborhood is the delta neighborhood and the outer neighborhood is the epsilon neighborhood. So if you pick the initial condition from the delta neighborhood, and you can your trajectory of the system immediately follows or belonging to the epsilon neighborhood. So then we can say that the stability in the sense of Lyapunov. So the next definition 2, so which is nothing but the finite time stability. So consider an initial time t naught. So this is the definition due to Francesco Amato. So he was a French mathematician. He has used this definition. So consider an initial. He is the person who introduced this definition. So for the study of finite time stability. So consider an initial time t naught, a positive scalar t, two sets psi naught and psi t, such that the given system 1 is said to be finite time stable with respect to these values. If x naught belongs to psi naught, which implies that x of t belongs to psi t. So for all t naught, for all t belongs to t naught plus t naught comma t naught plus t, where x denotes the solution of the given system 1 starting from the initial condition x naught at time t naught. So we have the another definition, fixed time stable. The additional thing is we can calculate the settling time t max. So if it is finite time stable, and also we have a settling time function t of x naught, so we want to calculate t max. So there is a real number t max positive such that the t of x naught is less than or equal to t max. This is true for all initial conditions. You can vary the initial condition, your t max will be fixed. So we want to estimate the settling time for fixed time stability. So next one, prescribed time stability. Say consider system 1 is prescribed time stable if it is finite time stable, and we have the settling time t star is a preset positive constant. So you have to fix. So we have to fix the constant t star. So previous case for a fixed time stability, for a definition of the fixed time stability, we have to calculate the settling time. So where in the case for a prescribed time stability, so we have to fix the t max value. So that is t star is a preset positive constant. If it is, that is, if it is finite time stable and the convergence time can be arbitrarily specified, here t star is also called the prescribed time. So on the another definition, predefined time. So for the system parameter rho and the constant t max, the origin of 1 is said to be predefined time stability for system 1 if it is fixed time stable, and the settling time function we have the settling time function, and the t of x naught is less than or equal to t max for all x naught belongs to Rn. So in this case also we have to collect we have to check all the for all the initial conditions we have to check this condition. So then this t max is called the predefined time. So as a consequence, the finite time stability and the Lyapunov stability are both of them are independent concepts. Indeed, a system can be finite time stable but not stable in the sense of Lyapunov. So vice versa. So this is true. Obviously, this is true. So suppose you have to take a system having oscillation. Suppose for a particular time the system will be stable. Where in the case, suppose you have to take the same system the same system cannot be converged to your equilibrium point. So in this case, so the system is not stable in the sense of Lyapunov, but it is finite time stable. Why? Lyapunov stability deals with the behavior of a system within a sufficiently long, that is infinite time interval. The finite time stability is a more practical concept useful to study the behavior of the system within a finite interval. So the finite time stable focuses on achieving stability within a finite amount of time. Fixed time stable, it mandates the stability. So as we have defined in the finite time stability concept, mandates the stability exactly at a predefined point in time. So here we want to estimate the settling time. So the third definition, predefined time stability, encompasses both finite time and fixed time stability and denotes the stability within a predetermined time interval. Prescribed time stability is not well established term, but it could refer to setting specific stability criteria within a designated time frame. Okay, here we have to consider, we have to study the finite time stability analysis of continuous time linear time varying system. So in this section, on stability analysis, we will explore the attainment of FTS for linear time varying systems. Here you have to consider a system, linear system, x dot equal to x a of t, x of t, with respect to the initial condition x of t naught equal to x naught, and a of t is matrix from r power n by n, is said to be finite time stable with respect to t naught, with respect to the constants if x naught transpose r x naught is less than or equal to 1, then this implies that x of t, x transpose of t, gamma of t, x of t is less than 1. The assumption gamma of t naught less than r guarantees the closed ellipsoid. So this is the closed ellipsoid, is a subset of the open ellipsoid, this one. So the main concept, the following theorem gives the necessary and sufficient condition for the finite time stability of the given system. The statements are, the following statements are equivalent. System 3 is finite time stable with respect to T naught T or gamma of naught. This is nothing but the definition due to Francesco Amato. So for all, if it is true, then for all T belongs to T naught comma T naught plus T, phi of T naught. So this phi is nothing but the solution of the given linear system x dot equal to A of t into x of t. So this to be less than r, where phi of t naught is the state transition matrix. So it is nothing but the fundamental matrix, fundamental matrix of the linear system. So the matrix valued function w of t naught, the solution of the differential Lyapunov equation. So this is the Lyapunov equation, and we have a derivative. So therefore this is called the differential Lyapunov equation. Is positive definite and it satisfies this condition. So if it is true, then we can say that these statements are equivalent for the definition of finite time stability. So on the fourth one, either one of the following two cases holds. So you have to take this condition or this condition. Say any one of them is true, then the statements are equivalent. So and also in this case we can calculate the positive definite solution of the matrix differential equation. So this is the Lyapunov equation. Lyapunov differential equation. So this equation also having this equation can be solved, and then we can have the solution. So the solution also finite time stable. So this is the fifth condition. So these 5 conditions are equivalent statements for a continuous system to be finite time stable. So this is the main result of our study. The Lyapunov conditions for finite time stability of linear time varying time delay system. In this case, so we have considered for both integer order system as well as the fraction order system with this in the sense of coupled derivative. So consider the general time delay system x of t equal x dot r if t equal to f of t comma xd. So it is a functional differential equation with respect to the initial condition. So the condition is nothing but the initial function. So it is this denotes the x dot denotes the right hand derivative of x, and your t naught is 0, and your f of t comma phi is a map from minus tau comma capital T to cross c tau to Rn. Is a known function and it is constant and it is locally Lipschitz. So if it is Lipschitz, then only we can have a unique solution. Okay, so that's why we can assume, so this nonlinear function having must satisfy the Lipschitz condition. Okay, so we have the definition 7. So given 3 points T, C1 and C2, C2 greater than C1, the system 15 is said to be finite time stable with respect to this constant if norm phi tau is less than C1, which implies that the norm x of t is less than C2 for all t belongs to 0, t. So the next definition, finite time stability for finite time contractive stability. So in this case we can have another one more constant. So comparing to the previous definition, we can have another one more constant. So the constant also involved in this definition. So if it is finite time contractive stable, so then for all initial condition is less than C1, then norm x of t is less than C2. Moreover, norm x of t is less than eta also. So this is the new parameter. So for this new parameter we have an additional condition. So this condition also holds. So the system is said to be finite time contractive stable. So these conditions are to be hold. So this is the exact figure for the FTS as well as the FTCS. So it is the illustration of FTS and FTCS. So in the first case, so you have to take the blue and red color trajectories. So the blue color represents, so if you choose the initial condition here, so it moves, the trajectory of the trajectory moves in the outer orbit, so it is stable, finite time stable. So in the case red line, it moves in the inner orbit, it moves to the inner orbit, so therefore it is finite time contractive stable. So the definition 7 describes the fact that the state variable starting from the given initial state do not exceed an assigned threshold in finite time, so which is displayed in the blue curve. So while definition 8 describes the contractive dynamics in the finite time context. So namely, besides staying in a certain specified threshold in finite time, the state variable will be within a specified bound, so which is smaller than the initial state before reaching the terminal time. So it is represented in the red curve. Hence, finite time contractive stability is a much more stronger requirement than the finite time stability. So these are our theorems. So we have derived for finite time stability as well as the finite time contractive stability. In the sense of we are constructing the Lyapunov-Razumikin method. So the theorems are derived. And in this case you can consider the time varying time delay systems. So here we have the time delay. So suppose you have to take the system x dot equal to a of t into x of t plus b of t into x of t minus 1 t minus tau. This is the time delay term. So with respect to the initial function x of t equal to phi of t where t belongs to minus tau comma 0. So in this case the same thing can be implemented, the previous results can be implemented to this problem. So we have derived some sufficient conditions for finding the finite time stability as well as the finite time contractive stability. So here we construct a Lyapunov function x transpose of t x of t, and we have to take the derivative of this Lyapunov function, then the derivative should be less than 0. We can attain this inequality. We can attain this inequality. So it is a sufficient condition for finding the systems to be finite time stable. Yeah. So this is the proof of the theorem. Now we move the finite time stability for a fractional order system. The fractional, here we assume we are taking the fractional derivative in the sense of Caputo. So there are so many definitions are there. So there are plenty of definitions are introduced for defining the fractional derivatives. But we took only the Caputo derivative. It only, the reason is it has only the application, some physical applications for Caputo derivative. So other derivatives can have or cannot have. So we are not concentrating any such derivative for deriving or for developing our theoretical results. So here we consider the nonlinear fractional order differential systems with respect to the initial condition, and we derive the theorems. We use the same stability definition in the sense of Francesco Amato, and then this is the definition for finite time contractive stability. So we derive the fractional order Lyapunov-Razumikin condition, sufficient condition for the finite time stability as well as the finite time contractive stability while using the Lyapunov-Razumikin condition. And these are the conditions have been derived. So here we have to construct a Lyapunov function, and these are our results for the fractional order systems. So then the condition 1, 2, 3 for satisfies, then the system is finite time stable as well as the finite time contractive stable, so which includes the condition 4. Yeah. So while dealing with the finite time contraction stability, we have two more constants to add in the definition of finite time stability. So same thing. So here we consider the fractional order time varying time delay systems. We want to derive the sufficient condition for the system should be stable, finite time stable as well as the finite time contractive stable. So we have the conditions, condition number 1, 2. So with this we prove that we construct a Lyapunov-Razumikin function v of t comma y of t equal to y transpose of t p of t into y of t, where p of t is a positive definite matrix. So the conditions are, we have to take the fractal derivative for the function v of t, so and then we can achieve our results. So then this condition holds, so then we can say that the left hand side is less than or equal to rho of t into I. So this is the condition, so as defined in the statement of the theorem. Yeah, the defined statement of the theorem. So if it is true, then the system is finite time stable. Okay, so we have another one more thing. If we are adding another 2 more constants, then we can achieve the finite time contractive stable. So we have the numerical example. So we have considered 2 examples. So one is the ball motion basic ball motion model. So that this model is defined here. So this is the basic ball motion model. So in this ball motion model, we can include a time delay. So in this case, we can evaluate the system behavior for different fractional orders, 0.9, q equal to 0.9, 0.8, 0.7, 0.6. So in this case, suppose while you are comparing with integer order systems, so it is these curves shows that it is an interpolation function. So if you have different fractional order, it gives different results. So it is nothing but we studied in numerical analysis the interpolation function. So it shows the same thing. So by using the concept of FTS, the main objective is to determine the velocity of the ball over finite time interval, and also find their minimum values with respect to the different fractional orders in 23. So here we assume the time delay is 0.55 and capital T equal to 5. So your finite time should be 5. the velocity of the ball can be evaluated using theorem 8 as v of t is less than 16 minutes meters per second. So for t belongs to 0, 5. Also the velocity of the ball estimated through FTS condition, v of t is strictly less than 8 meters per second in the time t belongs to 3.5 to 4.5. So these are shows in the figure. Also, so the minimum value of the trajectory is obtained faster as we reduce the fractional order in t belongs to 3, 4 as shown in the above figure. So at order q equal to 0.9, the minimum of x1 of t lies 3.77 to 3.87. So where order q equal to 0.8, the minimum of x2 of t lies 3.64 to 3.74. When we reduce the order q equal to 0.7, so your x3 of t, minimum of x3 of t lies 3.5 to 3.60, and the order q equal to 0.6, minimum of x4 of t lies in 3.38 to 3.48. So we have another one more example. So let us construct a time varying system like this: C of t equal to this matrix 2 by 2 matrix as well as D of t equal to the 2 by 2 matrix. So then we assume k1 equal to 3.62, k2 equal to 22, t9, delta 3.5 and epsilon 1. So pick n of t equal to 0.01. So the system 22 is said to be finite time contractive stable. The theorem 9 corresponding to the conditions which shown in the below figure. Yeah. So in this case, the system, these are the system behavior or the solution trajectory for the given system. So it converges in a finite time. So take a time varying fractional order system in 2 dimension. We solve it with the FTCS conditions. So the solution trajectory are plotted in this figure. So for the fixed values 5, 2, 2.4, 0.4 and 0.5. Okay, thank you. Any questions?
So here we have dealt with finite time stability and finite time contraction stable. So in the existing literature, I have gone through that finite time stability is obtained through both Lyapunov-Kravatsky function and Lyapunov-Rosimsky function. So my question is it possible to obtain the finite time contraction stable through Lyapunov-Rosimsky function or Lyapunov-Kravatsky function? Sorry.
Yeah, this is the theorem which was derived using Lyapunov-Rosimsky theorem.
No, sir. Is it possible to obtain through Lyapunov-Kravatsky function?
Krasovsky. No, it is not possible. So the reason we derived and we derived some theorem, so we want to prove these results with the Lyapunov-Krasovsky, but we have some struggle facing. We have faced some struggle, so then we drop it.
Oh.
So these theorems, these results only valid for the finite time stability as well as the finite time contractive stability due to the definition of Francesco Amato, which falls under only Lyapunov-Rosimsky. So we cannot extend these results to Lyapunov-Krasovsky method.
So the main struggle deals with constructing that Lyapunov function.
Yes, yes.
Thank you.
Suppose you have so in this case we can use only quadratic function. Only quadratic functions. You have not used any the functionals involving with time delays. So it is not possible. You can include the integral terms involving time delays. So it is not possible.
So, sir, can you please explain the concept of finite time contractive boundedness?
Yeah. So this is the so in this case this was introduced by Francesco Amato.
Okay.
So this definition was introduced by Francesco Amato. So the finite time stability is a finite time boundedness. So you can use, so the system is said to be bounded. So in this case the system is bounded. So you have a nonlinear system, the nonlinear functions would be bounded.
So here there exists
Since it is continuous as well as Lipschitz continuous, so then we can assume that the nonlinear function is bounded. So then automatically if you want, if you define a finite time contractive stability for this system, automatically it becomes a finite time contractive boundedness.
Thank you, sir.
Is there any other query, please?
You said you have faced some problems in constructing Lyapunov-Krasowski.
No. So we are taking only the quadratic function, but the results of the theorem does not hold. So we want, if you want to prove the theorem, so you have some, you are going to face some problem while proving this theorem. So in this case we proved the theorem, we are assuming a contrary, and then we proved the result which is not hold, then there is a contradiction. So then so our assumption is wrong. So hence we can conclude like that. So in the both cases you cannot directly prove that result as well as indirectly.
All this happened in the case of continuous time. Does all that problems occurs in when we consider discrete time case? For discrete time case also.
Yes.
Okay.
So your question.
All those problems occurred in the case of continuous time.
When we are proving the same result, if you are applying discrete,
same problem.
So the Lyapunov-Krasowski functional, the method of Lyapunov-Krasowski is not. I think it is not possible for the finite time contractive stability.
The problem may be occurred in solving integral terms in quadratic terms. When we consider summation terms.
When we are including some more terms in the Lyapunov functional, so it becomes very it creates more problem.
Okay, thank you.
Any other query, please? Okay. It was a nice lecture, sir. Thank you so much.
Thank you.